Welcome everyone. In this video I'm going to test the TEC12710 Peltier cooler, and this is another freezing test. So what I will do, I will monitor the temperature of 100 grams of water inside an aluminium container, which is also inside a polystyrene box, so it's more or less insulated from the environment, and I will see how the temperature changes at a certain power level of this device. And what I did so far for the previous 3 units, I set the current to the level which was the level of the minimum cooling. So that was basically the current that was the minimum or the maximum that I could go, and I could reach the lowest possible temperature. So here for this 10 ampere unit it was 6.82 amperes, and that was able to produce us minus 21.9 degrees Celsius. So that's quite nice, but that was without any kind of heat load. So there was nothing attached to the cold side of the Peltier cooler, and the Peltier cooler was insulated more or less, so it did not have to pump heat, or not too much, and that means that we could maximize the DT value, which is the temperature difference between the cold and the hot side of the Peltier cooler. But here we cannot really maximize the DT because we have a heat load here in a form of 100 grams of water inside a 87 grams of aluminium container. So we have these two things attached to the cold side, and they have to be cooled down, and that takes some energy. So we will calculate how much heat we need to introduce to the system or remove from the system in order to cool it down to 0 degrees or further. So let's go through the setup. So we have the water cooling. It has a radiator which can accept 2 12 centimeters fans, and these fans are attached to the radiator in push configuration, so the air is pushed through the radiator by the fans. And we have 2 equipment here which I built. This is like a power and temperature meter combined together. So what this does, with the green thermometer, which is a K-type thermocouple, I measure the cold side, or try to measure the cold side. So that is basically the bottom of the tub, which is in contact with the cold side of the Peltier cooler, and with the white wire here I measure the back side of the aluminium cooler. So that is giving us some number about the DT. It's not a perfect measurement, I know, but at least we get the idea about the values. And then it also measures the current and the voltage applied on the Peltier cooler, and it logs it to an SD card so we can look at the data after I finish the video. And then we have this tiny box here, and that is measuring the temperature at 4 different spots. 2 thermometers, channel 1 and channel 2, are attached to the water system basically. So it is measuring the top of the tank and the bottom of the tank. I will show you a picture how it looks like. And then the third value will be for the water cooling system. So essentially it shows the same temperature as this, because this device measures the temperature here. And then we have a 4th value, which is basically the temperature of the air exiting the radiator. So we will have a lot of temperature values, and now we will also be able to measure and log the current and the voltage by our own device. So that's what we have here. And what I will do is basically I will just start up the power supply, because the pump is already running, as you can probably hear it. And then I just set it to 6.8 amperes, and then I wait, let's say 10 minutes, and see what happens to the water. And also I will turn on the logging, and we see what happens. So first of all, yeah, I have to notice that this experiment is far from perfect, mainly because we cannot stir the water. I just don't have the devices for that right now. So since the water is not stirred, it is stationary, and then the distribution of the cold inside the water, if I want to simplify the way of the spreading of the heat, or the way of the removal of the heat, then the way that the water gets cold inside this container is very bad, because the molecules are more or less at the same spot. Of course, they are moving around a little bit, but not that much as we would stir it. And therefore, roughly the same volume of water is at the same area all the time. And there is just a very little amount of self-stirring or self-diffusion, and also a very little amount of heat conduction within the water. And due to this problem, there will be some certain areas which are cooled much quicker, and those are the areas which are in direct contact or very close to the wall of the container, and which are right above the area where the Peltier cooler touches the bottom of the container. And I showed this to you in my previous videos. If I can remove the ice from this one, I will show it to you here at the end of the experiment. But I have to notice that the cooling is not perfect because of the lack of stirring. So we will not get some numbers that you can rely on really, but it's a very good demonstration. So everything is at roughly 28-29 degrees Celsius. That's quite nice. So I just turn on the logging, and then I just see what happens with our experiment. So this is on, and this is on, and I turn on the power supply, and we go until we reach 6.8 amperes. So according to this device, it shows 7.2, but that's not always the reality. So .9, so I can decrease a little bit. .81. We are very much satisfied with that, and 7 is shown here. That's the difference between the different principles, how this thing inside this box gets the readings for the current, how this device gets it. This is basically a transformer, and you put this conductor inside the transformer that induces a magnetic field, and the magnetic field is basically captured by the transformer, which converts the magnetic field into a voltage, and that voltage is proportional to the current passing through the wires, and that's how we measure it. And inside this box we have a Hall sensor based detector, which is also somewhat similar. So there is a copper wire on a printed circuit board, and as the current passes by the copper wire, which has an integrated circuit above it, so as that IC sees different magnetic fields, due to the Hall effect, it can give some proportional voltage, and that output voltage is basically proportional to the current flowing through the circuit, and that's how we basically measure the current with that kind of sensor. And this device shows 14.3, and the power supply shows 15.1. So also there are some differences between the voltages, but it's not significant. So let us run the system for a while. Now it's 40 on the watch, and we come back in 10 minutes, let's say, and we see what happens to the system. So a little bit more than 10 minutes has passed, so we can check all the numbers, and what I can see is that the temperature of the cold side is at 1.6 degrees Celsius, And in fact I can see some ice forming around it, so that's like pretty much correct. But then if we check the other two thermometers, which are the black cables here, the top one is showing 1.7 degrees Celsius and the bottom one here is showing 2.2 degrees Celsius. So that's pretty much close to the freezing temperature of the water. So we can see that this device is maybe even faster than the previous one, the 8 ampere unit. But we will see it better when we look at the charts. And the current and everything is the same as it was in the beginning. So if I would measure it, I should get the same numbers, and why not do that? So here we see 6.9 amperes. And this guy shows 6.7. That's a little bit below the required current or desired current, but you can change it slightly and see if we could reach that number. Sorry, yeah, 6.82 something. We accept that. So this shows a bit different, 7.2, 7.1 and 14.7 volts. But yeah, but I see ice forming in the container already, so that's very nice. So let's wait 10 other minutes and see what happens with our temperatures. So we are back, and I can see that around 30 minutes passed since we started the experiment. And what I can see here is that the K-type thermocouple is at minus 0.7 degrees Celsius, and the two thermometers are 0.0 and 0.0 Celsius according to these two numbers on the screen. The water temperature is 35 degrees, that's very nice. So that means that we haven't really heated up the water. And I'm glad about that, because the power is 105 watts, which is just the power coming from the heating effect. And that is still not sufficient to significantly increase the temperature of the cooling water, and that is very nice. And if I check the water inside the container, I can see that there is more ice in it, but still there is a lot of water. So if I knock this box, I can see that the water is like moving around. So let's wait 10 other minutes and see how the temperatures are going. Alright, so I was waiting more like 20 minutes, but the temperatures haven't really changed. The thermocouple went down to minus 1.8 degrees Celsius. So according to the differences measured by the thermocouples, the DT is around 40. So we are more like around 15 to 60 degrees Celsius regarding the DT. And that's what our measurements suggest as well for the voltage values and the current values. So that's what we get there. And also the other thermometers are showing minus 0.8 degrees up here, and down here is minus 1.2 degrees Celsius. And now the test is running for like 50 minutes in total. So maybe in 10-15 minutes I will stop the experiment and we see how our curves look like. But so far what I can say, most of the water is ice, but I can still see some liquid water, so that will probably not freeze in 10 minutes, but we will see. So I will come back around in around 10-15 minutes, and then we conclude this part. I will try to remove the ice, and if I don't succeed, then I just simply go to the computer and do some calculations and analysis on the data, and that's all for the TEC12710 unit. So we are roughly 10 minutes after the previous cut, and I can see that both of these thermometers are showing minus 2 degrees, minus 2, minus 2.2, and minus 2.7 on the thermocouple, we can do another check. So I will use this infrared thermometer and measure the top of the ice, which is very cold, -7. So I measured the area which is in contact with the cold side of the Peltier cooler, of course. So that's a bit of a cheating. And what I can see, there's a little bit of water here and there, but most of the water is transformed into ice now. And you can see that the temperature is 35 degrees Celsius. That's the temperature running in this water. And basically that's all. But what I can see that this cooler is not as good as the previous, because if I compare the performance of this, or this is again just a qualitative comparison, but if I compare the amount of ice formed in this box as compared to the amount of ice formed in the box with the 8 ampere unit, then there was more ice previously than now. So this suggests that this is a bit worse for this purpose, or with these settings, I would say, because as I said several times, a lot of things depend on the cooling. So of course, if you cannot really maintain cold hot side or cold enough hot side, then your cooling performance will drastically drop. And as I showed it in the previous comparison video, where I just compared the minimum temperatures of these devices without any kind of heat load, we could see that the sweet spot of these coolers is the 8 amperes, because we can go the deepest with the temperature while having sufficient cooling with our cooling system, or providing sufficient cooling. And then below that, let's say performance, so 6 and 3 ampere units, we just could not benefit their cooling power properly. And about that, we could not benefit, so for the 10 and 15 ampere units, we again could not benefit the cooling power, because the heating which is coming from the current running through the devices was much more, and therefore we just could not remove enough heat, I think, at least. So yeah, we could see that this is maybe a bit worse than the previous unit, and I was running them for the same amount of time, and this was running 1.6 amperes higher than the previous. So yeah, so I think I conclude this part, and I will go and check what is on the SD cards. Hopefully our data is saved, and then I do some analysis and conclude the video. So I think I will not try to remove the ice at this point and in this video, because I see that there is still some water left. So you can see the data and some calculations here. So first let's look at the current and voltage chart. So that is here on the right hand side. So you could see that the current is around 7 amps, that's the red curve, and it's on the right hand side y-axis. So that was roughly 7, and the voltage was around 14 point something, let's say 14.5, measured at that point. It was interesting that if I measured it at a different point after the power meter, then I got 12.5, and that's more reasonable for me. So I have to check this. It's lucky that I always measure it with a different multimeter as well. So yeah, this is all, and here you can see a small jump, and that was when I slightly adjusted the current, because it changed during the measurement because of the temperature change, but that's not a big deal. And let's go to the temperature chart. So here is our main area of interest, around 12 minutes, let's say. And that's very disappointing, because the previous one was at 14 minutes. So not too much better, it's just 2 minutes. But what you can see here, there is a jump and there is a small change here in the, or noticeable change in the slope. So I would say that the phase transformation from liquid to solid starts here. So the nucleation of the ice starts here, and we cannot really move away from the 0 degrees as long as we have water in the system, liquid water. So, and you see that when we approach the end of the experiment, so let's say from starting around 40 degrees, we start to go below 0, and we really start to cool down the ice which surrounds the thermometers. And I just repeated some calculations. So this is basically the heat needed to change the temperature of the water by 29 degrees, and we have 0.1 kilogram or 100 grams of water, and this is the specific heat of the water, and this is just the delta T. So Q equals C times M times delta T, and we get the result in kilojoules if we use these units. And the same for aluminium, roughly the same mass, so just 13 grams of difference, but the specific heat is very, very different, so let's say a factor of 5 almost, and that's significant. So it's much more easy to cool down the aluminium and metals in general than water, and you can see it why. Of course, we started at the same temperature, that is basically here, up here, that's roughly 29 degrees, and then this is the result. So roughly 14 kilojoule, or roughly 4 watt hours is needed to cool down the water from 29 to 0 degrees. But of course we can say that this is the amount of energy which is needed to change the temperature by 29 degrees, because the same would be the result if you wanted to warm up the water from 0 to 29 degrees Celsius. It doesn't matter. As long as you don't have phase transformation, then you don't have to worry about these things. You just see the temperature differences. And then let's check what was the cooling power. So we applied roughly 6.8 or 7 amperes, and the DT based on the thermometers that I was using was roughly around 40 degrees. And if I go to the DT versus QC chart, then I just check it at 40 degrees, and I go up where I have the 7 amperes slope, that is roughly halfway between the 6 and 8. That makes sense, and that is roughly, let's say, 44, 43 watts. And if I do the calculation, then that suggests that if I can provide 40 watts power to a system which needs 3.87 for an hour to have this kind of temperature change, then it comes out that just in 5 minutes we would be able to cool down this amount of water. And this is not correct at all, because you can see that this is 12 minutes, so we are away with a factor of 2. And then we can do the following. So as I said, that the DT is usually underestimated by 15 to 20 degrees. So this comes down, let's say 55 degrees to 60 degrees. So let's say we are at 55 degrees, so we go to the DT versus voltage, and here it will be very important that I also measure the voltage with the different equipment. So 50, that should be somewhere here, let's say, 55, sorry, so that should be here, let's say, and then we have somewhere 7 amps, so we are between these two curves, so somewhere here. And that's almost perfect, because when I measured the other voltage, that was 12 point something, a little bit somewhere between 12 and 13, so let's say somewhere here. So that makes sense. And then this is just sort of a confirmation that if I was at really 55 degrees Celsius, my voltage should be something like 12.5, 13, somewhere here, and that is good. So then we can use this, let's say 55 degrees, to go back to the DT versus QC, and I go up to 55 degrees here, and then again I look to the look for the area between 6 and 8 amperes. That would be the 7, so somewhere here, and that's 24 watts. So this should, yeah, double roughly. So then that is, let's say, 11 minutes, and that makes sense. So that's pretty much close to 11. So again, we were so far off with the cooling power, and that is because of the one thing is that we cannot really control the system the way we want, and also the real DT is much higher than we would expect, and that's just from the fact how we cool the things. Of course, if we were able to remove the heat in a better way from the hot side, then we would be probably better with the results, but now this is what we get. And as I told you some several times, this kind of experiment is just typical for my own setup. So if you build a better, and why not, if you build a better cooling, and you can do that because now we know what are the errors, so probably I will do a set of experiment again, not for this kind of purpose, but something more advanced, and I can learn from these experiments a lot, and now I see what I need to improve with the cooling and so on. But you can also do this, so you can improve your own cooling system, and you can improve your own measurements and everything based on these kind of, let's say, failures or mistakes, and that's just good. So it's very good to learn from the mistakes. So it's a bit trial and error, yes, but still it works. So we learned here that the DT is very important, and it's usually underestimated by roughly 15 to 20 degrees. So if you measure your hot side, always add around 15 or 20 degrees Celsius, you will be safer with the cooling power that you can expect from the system. So yeah, but we are approaching to the end of this series. So this was basically the fourth device. So the next device will be the 12715, and I don't expect much better performance because that device produces a lot of heat, and therefore the cooler will suffer a lot because it's quite warm nowadays, so the room temperature will be higher than usual, but we will see the results. So I hope you learned something, and I hope that this video was useful and instructive. So if you have any comments or questions or some kind of suggestion, just please let me know, and I will answer everything. So I read the comments and I try to answer everything, not only with a short sentence, but really I want to be engaged in the discussion. So yeah, please write anything, and don't forget to like the video and subscribe to the channel, so that will help me a lot. And this is all, so thank you very much, and see you in the next video.